Honors Pre-Calculus students, this is Mr. Hale, and these are your 8.6 notes. And I'm not apologizing for this because it's a great lesson that you're going to enjoy.
You know I try, but I don't do too well with apologies. I hope I don't run out of time, cause someone call a referee.
Today we're going to be looking at probability. It's a bit of an extension from our studies of counting principles. There may be some surprises, but I think you'll probably like it. So we have some terminology here you can read. I'm not going to read it to you, but one I do want to highlight is the word sample space. We're going to see that one used quite a lot today. We're going to have to consider sample spaces of many problems. So let's start right away with that. Find the sample space for each of the following. One coin is tossed. Well, when we toss a coin, we have two options, heads or tails. And that would be it. But if we toss two coins, that opens up some extra possibilities. We could get heads and heads. We could get heads and tails. We could get tails and heads. Or we could get tails and tails. I should point out that when you're listing sample space, in this type of scenario, the order is really important, where heads, tails is distinguished from tails, heads. Otherwise, our probabilities don't work out properly. We'll talk more about that later on. We have one about Steph Curry coming up that hopefully will help clarify some of that if there are questions. Okay, one die is tossed. Well, our sample space there is just simply 1, 2, 3, 4, 5, and 6. Those are the options. And then finally, one coin and one die are tossed. Well, all right, this is our biggest set we've seen so far, but if you flip a coin, you could get heads or tails. So essentially, you could just pair heads with each of the numbers 1 through 6, and tails, which each of the numbers 1 through 6. And that would give us a sample space that looks something like this. So 12 possibilities in that scenario, heads and tails each paired with the numbers 1 through 6. Okay, probability. There's a lot of notation here that for some of us may be a bit confusing, but essentially it comes down to this. Probability is your desired outcome divided by total possible outcomes. It's always measured between 0 and 1. 0 is something that cannot occur. 1 is something that it's 100% certain. And we can also write it as a decimal, a fraction, or a percentage. Any of those are fine unless the problem specifies specifically one of the three types. All right, so a basketball question. Steph Curry is a 50% three-point shooter. What is the probability he would make at least, that's going to be a key word for us, 3 of 4 3-point shots? So I'm going to create a sample space here, and I'm going to start by defining some things. One of them is this. I'm going to use a circle to represent a make, and I'm going to use an X to represent a miss. Our sample space would look like this. Let's assume that he makes, well, I'm going to start with him making all 4 shots. But then, because there's a 50% chance on each one of them, it's equally as likely that he could miss the last shot, or maybe he'll make the first 2, then miss, then make, or maybe he'll make the first 2 and then he'll miss the second, or excuse me, the third and fourth shots. Like that. Basically what I've done here is I've exhausted every make option. There are other options though. He could make his first and then miss his second. And then he could make and make, or he could make, miss, and then I'm going to follow the order of the last 2. Make, miss will be here. Or he could miss the middle 2 and make the first and last. Or he might make the first and then actually miss the last 3. All right, our next column would be the situation where he misses the first shot but makes the second. So we could go a miss and then a make, and then 2 more makes would follow the pattern that we're seeing on the top row here. And then he could miss and make, and then make and then miss again. Or he could miss, make, miss, make. It's like Valentine's Day here in room 1004. Or he could miss, make, and then miss his last 2. Okay, and the last possibility is he could miss his first two shots. So we have to consider all these possibilities as well. Two misses, and then two makes, two misses, make, and then a miss, two misses, and then a third miss and a make, and then finally two misses followed by, well, two more misses. All right. So the question says, what is the probability that he would make at least 3 of 4 3-point shots? Well, the first thing we have to realize is, like for example, this group that I'm circling right here of 4 makes represents one event, okay, one possibility. So if we're thinking of it in terms of probability, that is one possible outcome. Now in this particular case, the one I circled is also part of the desired group, and I'm going to go through and find all the ones that have him making at least 3 shots. And that would be it right there. So we would say our probability of him making at least 3 would be 5 out of a sample space of 16. Now some of you may realize, hey, it said we could do this as a decimal, so if you want a decimal, I believe that's 0.3125. If you wanted it to be as a percentage, you could do that as well. So there's about a 31% that if you looked at any 4 consecutive 3-pointers he took, that he would make at least 3 of them. All right, onward. A card is drawn from a standard deck of cards. What is the probability that a jack is randomly drawn? Now remember, when we say standard deck, that means 52 cards. So what we're looking at is, well, how many jacks are in the deck? That answer is 4, 1 from each suit. Total number of cards, 52. And we can simplify 4/52 down to 1/13. Okay, 2 dice are tossed. What is the probability that the sum of the 2 dice would be 7? Well, let's think about it this way. Our sample space is going to be the case of us rolling perhaps a 1 and a 1, a 1 and a 2, 1 and 3, and so on until we got to the last example here would be a 6 and then another 6. So essentially our sample space is 6 times 6, or 36 possibilities. 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, and so on, all the way through 6 5 and 6 6. All right, now it says the probability that the sum is 7. Well, let's look at where we have desired outcomes. We could do a 1 and a 6. We could do a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. So 1, 2, 3, 4, 5, 6 possibilities. So our probability here is 6 out of 36, or simply 1/6. Again, if you wanted to change that to a decimal or a percentage, you'd be more than welcome to. All right, on number 5, you guys can read the question, but essentially a dodecahedron, the numbers 1 through 6 each appear twice. Think of it this way. What's the probability of rolling a 1? Well, it's 2 out of 12, which is exactly the same as 1 out of 6. So having a dodecahedron with numbers 1 through 6 on there twice does absolutely nothing to change the probability. So it's the exact same question we just answered, 1 and 6. All right, let's look at the next one, ACT scores. You can see the chart here, various scores. So what is the probability that a randomly chosen student from this group scored at least 28? Well, we got 3 groups of people here that scored at least 28, and you can see them right there. So we've got 118, 42, and 4, so that's 164. And the grand total number of students, if you add all 7 of these together, would be 966. And 164 divided by 966 would give us about 1.1698, or you could maybe call it a 16.98% probability of a 28 or better. Decent score. All right, 2 events are mutually exclusive if they have no common outcomes. For example, rolling 2 dice and getting a sum of 6 would be completely different than getting a sum of 9. There's no way you could get both of those sums at the same time. So they're mutually exclusive. Some events, though, there's overlap, or we say they share a sample space, so there's a chance for things to be counted twice. And so the probability of events A and B occurring would be the probability, or I should say A or B. It's the union. Okay, so the probability of A plus the probability of B, and then we have this thing right here. This always seems to throw people off a little bit, but we have to subtract the intersection of A and B. The reason for this is if something that happens in event A and something that happens in event B are the same, if they're the same event, then we are counting that same thing twice. And I'll show you with an example with cards in just a moment. Now, in this second version of the probability equation, you can see that we don't subtract, but that's because these two events are mutually exclusive. So, in other words, there's no overlap. So, let's see what I'm talking about here. On 7A, a card is randomly selected. What's the probability that it's a jack? Well, in the deck of cards, there are 4 jacks, so we'd say 4 out of 52 would be jacks, or a heart. Well, there are 13 hearts in the deck of cards. But here's the issue. There's one card that's both a jack and a heart. Right now, it's one of the 4 and one of the 13. I can't count it twice. It does count for something, but not for 2 somethings. So I got to subtract 1 52nd, and that would, of course, give me 16 52nds, and we could simplify that down to 4 13ths. Not all events have overlap, though. Like, what is the probability? The card is an even number, non-face card. I'm going to break this down into suits, okay? So the possibility of getting an even club would be 5 52nds, 2, 4, 6, 8, and 10. The probability of getting a spade that's an even number would be 5 52nds. Clubs, now I've forgotten which suits I said. Diamonds, hearts, whichever one I'm missing, that one would also be 5 52nds. The grand total here would be 20 52nds, or you could divide both those numbers by 4, and we'd have 5 13ths. Okay, so the probability there's nothing to subtract. None of these 5 are shared with this or this or this. And honestly, some of you would probably look at this problem and say it's a lot simpler than I made it. And if you thought that, you'd be right. Speaking of fairly simple problems, I have one coming up for you right here. We got a diagram that shows people being a little addicted to their phones. Not that any of you know anything about this, but what is the probability of someone who never goes more than 30 minutes without using digital technology? Well, there it is right there. Up to 30 minutes is the max. That's half this group. That means during these notes, many of you have already had your phones out. Shame on you. Put them away. Pay attention. All right, someone who never goes more than 60 minutes. Well, that would be 50 and the 17%. We can basically just add those together, and we have our total 67%. File that under, did you really need to teach that, Hale? Think we had it down already. All right, 2 events are independent if the occurrence of one has no effect on the occurrence of the other. And if that is the case, the probability of both events occurring would be the probability of A times the probability of B. We multiply the 2 probabilities. So for our first example here, we're using a computer generator or number generator, selecting 3 integers from 1 to 20. What's the probability that all 3 are less than or equal to 5? Well, the possibilities each time would be 5 that would be less than or equal to 5 out of 20 total, and we're doing this 3 times. So 5 out of 20 times 5 out of 20 times 5 out of 20, which we know, maybe to make that a little simpler, that 5/20ths is 1/4, so 1/4 cubed would be 1/64. So 1 out of every 64 times that would happen. 3 straight numbers that are 5 or less. Okay, in 2011, old news and probably not accurate numbers anymore, but 18% of 18 to 29-year-olds were on Twitter. What's the probability of 5 randomly chosen people within that group all being Twitter users? Well, the probability of just 1 is 0.18, If I wanted to find the probability of 2, I would have to multiply by 0.18 again, and then 0.18 again for the third and the fourth and the fifth. So really, I could just take 0.18 and raise it to the fifth power. It's a pretty small number in this case. I'm trying to punch it in right now. 0.000. Some of you may have gotten some scientific notation on your calculators. That's okay. But this is the number 0.18896, and there's a few more digits, but that's plenty for me. That's a really small percentage. Even if you think of it as a percent problem, this would be 0. Move that decimal 2 places, 0.19%. Okay, way less than 1%. Now again, I would imagine that number has changed significantly over the last 4 years. All right, Powerball. Hey, you guys had a problem just like this on the homework. I'm going to work through this one kind of quickly because it's very much like the example that you can actually see from page 613. We have exactly one possibility that's a winner, and it's 1 over 59C5. 59C5 represents choosing 5 of the 59 white balls. And then you could do 35C1 for the red Powerball, or just make it simple and say that we know 35C1 is 35 because there's only one winner out of the 35. And you can see we're going to get pretty small probability of winning this lottery. So there's only one winning combination out of a possibility of 175,223,510. Kids, save your money. All right, last thing we're going to look at, there are times when finding the probability of an event can be fairly complex, but finding the complement can be somewhat straightforward and definitely a simpler option. And here's an example here. And by the way, the complement is just the probability the event doesn't happen instead of the probability that it does. And if you add the complement to the probability, it's always going to equal 1. So 1 minus the probability would give you the complement, or you could think of it as the probability is 1 minus the complement. So an iPad manufacturer has found that for every 5,000 iPads they produce, there are 2 that are faulty. The school district orders 150 for classroom use. What's the probability that at least one will be faulty? Okay, at least one's a key phrase here. That means there could be 1, there could be 2, on up to 150. That's a very complex thing to calculate how many will work. So instead we're going to say, what's the probability that all of them work? And then whatever's left would be the probability that at least one doesn't work. So here's what I'm going to think about. The probability of 1 working would be 4,998 over 5,000. The number that work divided by the total. There are 150 of these going into the classroom. I have to multiply this number together 150 times. This one, the first one, has this probability. The second one has the same probability. And third and fourth and so on. So we have to raise that to the 150th power. My calculator's telling me that 4998 over 5,000 raised to the 150th is about 0.942. And remember though, that's the probability of the complement of A. Now the probability of A, or the probability that at least one of these doesn't work, would be 1 minus 0.942. So we'd be looking at 0.058, or you might think of it as about 5.8%. All right, folks, that's your lesson. I think probability is one of those topics that's an interesting one. It's something a little different, although it's very closely connected to our accounting principles. It's also one that at times can be a bit counterintuitive. It doesn't come easy for everyone, and I would probably be included on that list. So don't feel bad if you have to put a little work in here, but I think I've given you pretty good examples that should help you along the way. Have a fabulous day.